we are starting our very last unit. Yay.
So we're skipping unit 9.
We did not skip unit 9. Technically, we did unit 9 already first semester when we did systems. If you remember, like right at the very end before final exams, we squeezed some system stuff in, but then we didn't have a test over it. We had a quiz, but we didn't have a test.
You were like, I wouldn't spend time reviewing it if it wasn't important.
Mm-hmm. Yeah, that was that first semester stuff. So chapter 10, last chapter. If you guys look at that yellow paper, next Tuesday is your last quiz.
Next Tuesday?
Next Tuesday is the last quiz that you have to take in this class. Last quiz. And then your test over this unit will be Thursday, May 5th. We're going to be talking about sequences. Good. Hopefully it feels mostly like review. So what is a sequence? Does anybody remember what a sequence is? 2, 4, 6, 8 is an example of a sequence. Can anybody else give me an example of a sequence? It is. Yes. A sequence is a list of things, usually numbers, that are in order and have some type of pattern.
Did you read like the sheet for it?
Nope. You got to write it down in your notes.
Really?
Mm-hmm.
That's all you know.
Can you do that for us, please?
I do that when we have story problems and graphs.
We're not going to have to graph.
Not today.
I'm glad we do. I'm glad.
A sequence is a list of things these things are usually numbers that are in order. All right, so for example, three, 5, 7, 9, on and on and on. That would be an example of a sequence. When you're looking at a sequence, you can usually tell it is a sequence because it has curly brackets around it. Curly brackets get used around sequences. We list the terms and we refer to them by number. So this one right here, this is my first term. This is my second term. Third term, fourth term, so on. What do you think the ... means? Yep, it goes on forever. This is an example of an infinite sequence. The nth term just means any term in the sequence that we want. Any term in the sequence that we want. There are two types of sequences that we're going to talk about right here, infinite versus finite. An infinite sequence would do what? Go on forever. And so a finite sequence would end. It stops at some point, yes. Not sure. Infinite sequence goes on forever. Finite sequence stops at some point. Infinite sequence notation. So for our infinite sequence notation, it's always going to be in order, so it's going to start with the first term, and then it'll give us the second term, and then the third term. The nth term is in there somewhere. It's whatever term we want or we're looking for or we're interested in. The formal definition for an infinite sequence. It is a function. What's a function again? What's a function? Every input has one output. This is a function. Function. Oh, this definition is for an infinite sequence. A function whose domain is the set of positive integers. Give me an example of a positive integer. 2. Give me an example of something that is not a positive integer. -2. Give me a positive example of something that is not an integer. 2.5. Yes. Is 0 a positive integer? 0 is not technically positive nor negative. It's the dividing line between the two. So 0 is neither positive nor negative. So when we say the domain is the set of positive integers, 1, 2, 3, 4, these are our counting numbers. The input can only be whole counting numbers. Because remember, this is where it falls in line. Last thing that we're going to write down before we go to some examples. I should probably do that in a darker color. A sequence has a rule. That would be the function rule. A sequence has a rule used to find the value of each term. So sequences are usually numbers. They're in order. We have a rule to tell us how to find the next term in the sequence. And if we're talking about the nth term, that would just tell us how far into our pattern we're going to go. We think of n as like our input, like our x's. The input can only be what type of numbers? What'd you say? Positive and integers, whole counting numbers. Those are the only types of things that our function rules can take when we're talking about sequences. Sequences get used in a lot of real-world applications. Like if you're thinking about seats in a theater. Usually each row behind has more seats than the one in front of it because it kind of expands out in a wedge shape. And there's usually some type of a pattern to how many seats they're going to add in each row. The rows would be the input. That would be where it falls in the sequence. So just like you can't sit in row 9 3/4, you cannot have an input value that is something like that. Does that make sense? Okay. Let's practice finding some terms in sequences. We're going to find the first 4 terms. What does n stand in for again? Any term in the sequence that we want to find. So these n's right here, term number we want. So if I'm trying to find the first term in the sequence, A1, what would I put in for n? 1. So I'm going to have 1 over 1 plus 1. So what is the first term in this sequence? 1/2. Let's go find the second term. I'm going to use the shorthand A1, A2 moving forward. I'm not going to continue to write down first term, second term, but I want to make sure that we know what I mean by A1 and A2. You guys okay with those? Okay. How do I find the second term? Okay. What are we going to put in for n for the second term? 2. 2 over 3. How do I find the third term? So what is my third term? 3/4. What about the fourth term? 4/5, yes. So I could write out the first 4 terms in this sequence as 1/2, 2/3, 3/4, 4/5. I would not close the brackets right here. Why would I not do that? Because it goes on forever. I can close them after I put that ellipsis. That means it goes on forever. So there's my first 4 terms. You guys might need a calculator for part B, but I want you guys to find the first 4 terms for part B. What is the first term in this sequence? 2.1. What is the second term in the sequence? 2.01. Third term? 2.001. And the fourth term, 2.0001. And it continues on. You guys feeling okay about these? I'm going to put up another one. I want you guys to find the first four terms. This one's a little bit more complicated. Find the first four terms for part C. Find the first four terms for part C. Yes. Yes, that -1 with the exponent on it is being multiplied to the fraction there. Yeah. So right here, you'll multiply those things together. is this out here controlling? Positive or negative. All it's doing is controlling the sign. For the first term, is it going to come out to be positive or negative? Positive. Because I've got -1 squared, that's going to give me a positive 1 there, times 1 squared is 1 over 3 minus 1. What is 3 minus 1? 2. So I have 1 times 1/2. This first term is what? 1/2. So the first term in this sequence is 1/2. Is the second term going to be positive or negative? Negative. Because I would have 2 plus 1, -1 to the third power is -1 over 2 squared, or sorry, times 2 squared over 3 times 2 minus 1. So -1 to the third power we said was -1 times, what's my fraction? 4 over 5. So -1 times 4 over 5, so -4/5. Will the third term be positive or negative? Third term's going to be positive. Fourth term will be negative. What is the third term here? 9 over 8. And the fourth term? -16 over 11 is correct. There's one more that I want to look at with you as we do this. Let me get the rest of this written down. All right. So I keep writing above these that what they give us in these brackets, this is our rule to find the nth term. What do we have on example D? Just 4. So the first term in the sequence is 4. Second term would be 4. Third term, 4. Fourth term, every term in the sequence is 4. My curly bracket got away from me. All right. If you ever saw a sequence graphed, it might have a linear shape, or it might have an exponential shape, or it might have some of these different shapes, but it's not going to be connected. It's just going to be individual points, because remember, the domain, the input, is only positive whole numbers. So it would just be those individual points, but you might be able to recognize a pattern from it. All right. We're going to start talking about recursively defined sequences, and we'll continue this discussion tomorrow. It's a big word that sounds scary. In practice, it's not as intimidating. The recursive definition of a sequence gives the first term so A1 together with the rule to obtain any term from the preceding term. We call this A k plus 1 from the preceding term which we call A sub k. So I'm going to show you some examples of recursively written sequences or recursively defined sequences. We're going to find the first 4 terms again, and then we're going to learn how to write the rule so that we could find any term, even if we don't know the one that comes right before it. What we were just looking at is when we have the rule so we can find any term in the sequence. All right, I'm going to put our example up here. You guys okay if I flip to the next slide? Okay. Here's an example of something that has been recursively defined. What is the first term? 3. What comes next, this part right here, is telling me how to find the next term. So if I know that A1, first term is 3, if I wanted to find A1 plus 1, so all I did here was I took K and I put it in here. This will let me find which term in the sequence. Second term in the sequence. That is equal to 2 times the first term. So I'm putting 1 in the place of K here. So A2 is equal to 2 times, what was A1 again? 3. 2 times 3 gives me 6. So here's the first term. Here's the second term. How would I find the third term then?
How is it 3?
How is what 3?
How'd you get 2 times 3?
That's what our rule says to do. This right here. So I have taken 1 and put it in the place of K right here. So 1 plus 1, this will find the second term in the sequence.
Okay.
So I have to do 2 right here times, remember I put 1 in the place of K. So that's A1. The first term in the sequence was what? It was 3. A recursive definition says I have to know the one that came right before it to find the next one. Yes, sir?
Where is this 2 coming from?
Right here. This is our rule. The rule says take 2 and multiply it by this term. For this first example, I put 1 in the place of k in both of those spots, right there and there. So far, so good? All right. So the next term in the sequence would be the third term in the sequence. To find, so I'm putting what in the place of k now? 2. So we're going to do 2 times what?
For finding the third term, I don't get why we're not using 3 for k.
Because k, look, this says if I'm going to find the third term, I need a 3 right here. I need to know the one that came before it. This isn't the same as what we were just doing. What we were just doing said I can pick out any term number and put that in for n. With a recursive definition, I specifically, like the only way I can know how many seats there are in the 18th row is if I know how many are in the 17th row. If I know how many are in the 17th row, then I have a rule that says, okay, add on this many.
So we find A3, so we gotta use 2.
Yes, we have to use the second term to find the third one. So I need A2. So this will find the third term in the sequence. So 2 times, how did we find A2? Yeah, 2 times A1, so 2 times 3, right? I promise there's a reason I'm writing it like this. What is 2 times 2 times 3? 12. So the third term in the sequence is 12. Yep, try to find the fourth one now. What is the next term in the sequence? 24. So we do 2 times A3. How did we find A3? It was 2 times A2, right? And how did we find A2? 2 times A1. And A1 was 3. Fourth term is 24. Here's why I wrote it down like this. What else did they ask me to do? It says find the first 4 terms and what? And the nth term. I need a rule to be able to find any term without knowing the one that came right before it.
Double it.
Double it, yes. Double what?
The term before.
But if I don't know the term before? What if I wanted the 50th one in this pattern? Do you guys want to go all the way up to 49 to be able to figure out the 50th one? Or do you just want to be able to pop 50 in? We could take this sequence all the way out, but maybe I want to know the 200th one in the sequence. It's going to take a lot of writing and a lot of math to get me there. I'm going to have to multiply a bunch of times, right? So to find the nth one in the sequence, what number stayed the same every time as I wrote down how we were finding it? The 2 didn't always stay constant. Here I have 1, 2. Here I've got 2. Here I've got 3. The 3 happened just once each time, right? And we're multiplying by 2, but how many times we multiply 2 by 2 depends on where we are in this pattern, right? So it's 2 to some power times 3. For the second term, how many times did I multiply by 2? N minus 1. Because for the third one, we multiplied by 2 how many times? Twice. For the fourth one, we multiplied by 2 3 times. So whatever n is, if I take 1 off of that, that's how many times we need to double it. We're going to pick up here tomorrow with this recursive definition. We'll practice with a couple more. Yes. Yes. Yes, sir.
So if we put 12 into A in this, okay?
If you put 12 in where? Right here? Yeah, you would work backwards, and you should get 3 as what n is.
How do I know what it is?
I'm confused. What are you trying to find?
The 2, the n minus 1, the power. I just feel like n is like all of a sudden a new
N is what this number is right here. N is this. Yep. So now I could find the 200th one in the sequence by just putting 200 in right there.
Oh, yeah.
Does that make sense? Yes. I've gone ahead and posted the homework. It is not due until, I want to say Wednesday night. I believe it's due Wednesday night. Okay. I'm going to say you can check on Canvas and see. We've got enough done that you can try most of them. We'll do more with the recursive definition tomorrow. Shh. Guys, when you're looking at the homework, if you get into it before tomorrow, any of the problems with a symbol like this we have not talked about yet. So you can't do those. Looks like a capital M on its side. You can't do any of those yet because we haven't talked about it, but we should get to it tomorrow.